right, we were working last time in section 3.2 with algorithms, and we had gotten to this one right here, and we alluded to this algorithm last time, but had not sort of explained it all out thoroughly. This is the left to right algorithm, and so let me show you how this works. And this is going to look like the kind of addition that you see in early grade school, where we're going to stack them on top of each other to do this. Okay. And instead of working from right to left, which is the standard algorithm, which we talked about last time, we're going to work from left to right. And for most of us, we're going to think, well, why would we do that? Well, why do you think it might be helpful for a child to work from left to right? Might be about whether they're right or left-handed. How you read. Okay, so this is sort of awkward that in English we read from left to right, but when we get to the math, we do it from right to left. It's kind of a strange phenomenon. I mean, why do we do it in that order? Kind of strange. So this gives you an option or a way of dealing with it if you don't want some student or some student has a really difficult time with this left to right issue, then gets another option. All right, so what we're going to do is we're going to add from left to right. So if I add 1 plus 3, what do I have? I have 4. And this is really what I did, is 1,000 plus 3,000. You can or you can not, I don't care, I mean, it doesn't matter, it's an optional thing, write down if that's what you added. But this is a 4. You can also either fill in zeros for these placeholders or not. You could just leave this blank, or if you so choose, you can put zeros here to indicate I didn't deal with that at all. I'm not done, don't worry. But I just did the first part. We're going to do the same thing, 5 plus 2, which is 7. And what I really did is 500 plus 200. So I really got 700. Again, you can put in the zeros if it helps you, or just don't. Okay? The next one is the 3 and the 1, which is 4, which is really 30 plus 10. And so again, if you would like, you can put in a 0 as a placeholder there because you didn't deal with that ones column. The last column is the one that I want to draw your attention to, and this is what will happen anytime you get a number bigger than 10. 4 plus 8 is actually 12, and I can't stuff the number 12 into one single space, right? So I'm going to have to make it bigger towards the left. It moves into the next place column. So I'll do another example to show you what I mean by that in a minute, but here's my 12 over here, so this was 4 plus 8. Now, you might say that I didn't get finished, but you almost are. Again, we're going to go from left to right, but the cool thing about it at this point is I don't have anything big enough that's going to carry over. I mean, that's the real kicker. I don't have anything almost in any column where I'm actually adding anything to it, right? Look at this. This 4 is a 4. This 7 is a 7. The only column where I'm actually adding is the 4 and the 1, but they're small enough, and they almost always are small enough. It's very few exceptions, again, where I would have issues with carrying over. Almost never. 4 and 1's 5. Right, so I did this down. And then I have a 2. So 4752. Let me change the numbers just a little bit so you can see what would happen if the number that had doubled up on itself had not been in the ones column. So let's see if I can make up the number and make it work. Oh, that'll work. All right, in fact, I don't even really need the last 7 and the 1. Let's erase that. Let's just do a 3-digit and a 2-digit. All right, so left to right, I'm going to start with the leftmost column. So when I do this 1, I'm going to bring, in essence, the 1 down, right? So this is really just like 100 here. I have 6 plus 7, and 6 plus 7 is actually 13. But the 13 has to be written in the column where there's a 6 and a 7, but that's a 2-digit number. So the 3 gets written here with the 1 over here on the other column. Okay, so you still have to line it up. It still has to be lined up properly, and if you need more place values, if you need more places for digits, it has to move to the left. And then you can have choices, just like these could have been zeros. Your choice to put a 0 there or not. And then the last one, 3 plus 3 is 6. And then again, adding from left to right, I have 1 and 1 is 2, 0 and 3 is 3, 0, 0 and 6 is 6. So here's a couple things. Some algorithms are good at explaining why something works. Some algorithms are efficient. That means they do something very quickly. Right? And then there's some algorithms that are convenient. This is that one. Right? They're convenient. They have this sort of a moving left to right idea that kind of matches with our idea of reading. And just in case you weren't aware, addition and reading are usually taught at about the same time. Right? So that's the convenience factor. Efficient, not so much. Right? This almost did double addition for everything, didn't it? All right? All right, let's do another one. This one has the effect of being efficient, but it's going to look different than you've seen before. So let me show you the lattice algorithm. The lattice algorithm, we put the numbers in just like before, 1894, 3218 above. Okay? And what we're going to do underneath it is we're going to draw a box. Okay? Draw a box. The box needs to be split into 4 vertical boxes. They don't have to be all the same size. They can be if you are OCD like me. 4 vertical boxes. What your boxes need to be then done is have them split like this. So there's the lattice description of the, or lattice word in the description. This is a really efficient method. It does things very quickly. It's pretty effective. It actually does a really pretty decent job at explaining why things are happening as well. I'll get to that point after we've done one of them. But let me show you. You can go from left to right, right to left. Won't hurt anything either way, so that's kind of cool. And each of the boxes underneath actually take the place value and they split it into the ones place and the tens place when you add numbers together. So I'm going to start, we'll just start on the left just so that you can see that it will work. If I have 1 plus 3, I get the number 4. The 4 gets written down here in the bottom part of the split box. Okay? 8 plus 2 is 10. So the 1 and 10 is on the top part of the box and the 0 and 10 is in the bottom part of the box. 9 and 1 also. 10, thanks. All right, so we put a 1 on top and a 0 on bottom. Don't scare me, guys. How about 4 plus 8? 12, 1 on top, 2 on bottom. Okay, so none of that had to do with whether I started on the left or the right, right? So that's kind of cool that you could start wherever you'd like. Pretty nice. And then what you do is you add up the diagonals. So here's one diagonal. This is the number 2. Here's my second diagonal, 0 and 1, which is the number 1. Another diagonal, 1 and 0, again the number 1. Last diagonal, 4 and 1. 5, and if I'd had something over here in the top box, it would be its own diagonal as well. This is your solution. So let me talk about why it works a little bit. What this does is, in effect, it does the carrying for you by grouping it with the next ones place or tens place that you were at, and grouping with the next place over. So it's doing the same carrying effect, but you don't see it written as an addition over on top. You actually see it written as in separate diagonal boxes. So lattice algorithm, good stuff. All right, scratch algorithm is our last one for addition. Can I switch my slide? Are we good? Okay. Scratch algorithm is practical in some situations. Okay, lattice, I could have done that for any 2 numbers added together, that's fine. Scratch has the feeling that it's used for when you're adding a bunch of things together. You notice how many numbers am I adding together here? 4. And so if you're thinking about something where you're adding, you know, a bunch of crowns here, to a bunch of crowns here, and a bunch of crowns here, and your crowns there, and your crowns in the back, we have a bunch of numbers we're adding together, that's scratch algorithm appropriate. Okay? Let me show you what scratch algorithm does. We're going to write all the numbers again from top to bottom, just like in, you know, early childhood. So we have 34, 18, 69, 87. And I'm not going to lie, this is probably going to take a little bit of practice because it feels a little bit awkward to do this. Okay? Here's what you do with the scratch algorithm. First of all, you got to work from right to left. Okay? Standard algorithm kind of working. What this does is it keeps you from having to count over 10. Okay, so let me show you. If I have 4 plus 8, basic addition facts, children have to at some point, or should at some point, have memorized 4 plus 8. Right? When they hit high school, they should not be going 8, 9, 10, 11, 12. you shouldn't be doing that. We would hope that you would know the 4 plus 8. 4 plus 8 is 12. Okay, but what you probably don't know is if I get the 12 and I've got 12 plus 9, that's not a basic addition fact. You know, think flashcard sets. Most flashcard sets don't have a 12 plus 9 card. Are you with me? Most flashcard sets add single digits together. You don't get a double digit plus a single digit. So here's what scratch addition does. We get 4 plus 8 is 12, and we scratch because we exceeded 10. And instead of thinking I have 12, we think I have 2. We ignore the 1 in the 12. We just think about the 1's digit, which was a 2. Okay? Why is that nice? Well, because I have a flashcard in my mind that says I know what 2 plus 9 is. 2 plus 9 is 11. Again, I've exceeded the number 10, so I'm going to scratch. Anytime I exceed the number 10, I scratch. Again, 11, and instead of doing 11, I'm not going to think 11, I'm going to think 1. That's the 1's unit. You have the units place. In the 1's place, I've got the number 1. So now I'm going to remember 1 plus 7 is 8. It really doesn't do anything different than our standard algorithm, except not make us count up past 10. Not make us know any addition facts past single digit plus single digit. That's what it does. And if you have a really long list of numbers, that's really helpful. So I don't know about you, but at some point I just start counting on my hands too, because I'm like, okay, I've got 43 and I've got to add 6 more, and 43 plus 6. I don't do that. I just start doing this. I start using my hands because at some point I don't want to add the numbers together anymore like that. So this is nice. What we do next is we count the scratches. How many scratches did I have? 2. So I carry over a 2. And then we're going to start the process over again in the 10th column. 2 plus 3 is 5 plus 1 is 6 plus 6 is 12, so I scratch. I scratched because I had 12. It was bigger than 10. When I have the number 12, I now ignore the 1, and I'm left with 2. And I have 2 plus 8, which is actually 10. All right? So actually, that got me to 10, which made me scratch. Which left me with the number 0. I don't have anything left. How many scratches did I make? 2. You can think about that as carrying over to the next column, although there's nothing in it. So this number is 208. Like I said, it's a really different way of thinking about this. I'm not going to lie. This one's a little bit challenging when you first start it. But it's very, very practical if you're dealing with a long list of numbers to not have excessive numbers of counting things going on. Okay? This is the scratch addition. All right, we're going to do some subtraction algorithms next. Are you ready? All right, first we're going to do the concrete model. We did a concrete model of these last time with addition. We're going to do a concrete model with subtraction. So to start with, let's see, where's my circle? To start with, we're going to make, whoa, not a circle that big. We're going to make my circle, and I'm going to put 34 in it. So I have 34 items in my circle, and I'm going to do that with longs and units, just like we did last time. So 34 means I'm going to have 3 longs and 4 units. So this is the number 34. And we're going to think about this like our model of takeaway. Do you remember takeaway? Okay, so we did 34. We took away 18. Or we're doing takeaway 18. Well, I can take away 18 as 10, 1 long, and 8 ones, right? 1 long, 8 units. And the 1 long is fine, but I don't have 8 units to take this away from. So what would I have to do to make that work? Yeah, I need to take my long and I need to break it apart in some way. Okay? So what I'm going to do next is, in essence, I'm going to take, let me just use a crayon. I'm going to take and leave 2 longs. So this is an equal picture. And I'm going to take the 1 long I had and turn it into 10 units. Okay, so there's my 10 units that were my original long. And I need 4 more units that were originally there already. These are equal, agreed? So then if I'm trying to remove, I need to remove what? 1 long and 8 units. So those are the pieces that are going to be removed. And my answer will then have what in it? 1 long and 6 units. And this is really good, and it can be done really well with blocks. That works really well. It can be done really well with money as well, especially if you're teaching something about money, and some of you will be teaching money in your classrooms, right? Can you imagine taking a dollar bill and turning it into 10 dimes? Yeah? We do this with my son when he gets fines. He gets fines for doing bad behavior, like not taking a nap at daycare and things. And he gets money for doing chores around the house. So we give him his money and then we take away his fines. Unfortunately, it doesn't work because he doesn't care, but it works really well for my daughter because she really wants more money. All right, but it has this feeling to it that I can say, here are your, $3 that you earned this week, and I'm going to take $1 and I'm going to turn it into 10 dimes, and because you have these bad behaviors, you owe me 6 of those dimes, and I take them away. Right? I mean, he earned them, and now he gets them taken away. So this idea of trading these numbers out can work with money just as well as it can work with blocks. All right, let's do another one. This is the expanded model and the standard model, which we saw an expanded model and standard model again with addition. So this is not that much different. Let me go back up here so you can see what they looked like. The expanded model for addition looked like taking, for instance, the number 30 and writing it as 34 rather than writing it as 30 plus 4, the number 10 and writing it as 10 plus 8, and then actually combining these in their values together. We're going to do the same thing. And then the standard algorithm, of course, you've seen before. So let's do the expanded algorithm. So I'm going to write the 30 plus 4, and I'm going to write the 10 plus 8. But I'm actually supposed to subtract. Okay, so to subtract means I need to subtract both of those values from the ones above, and we immediately run into a problem, don't we? Yes. You can deal with that problem in multiple ways, but if you're not dealing with negative numbers yet, you maybe don't have as many ways as you thought. That's
That plus that.
Well, in essence, you're changing it into a subtraction. So if you want to erase it and to rewrite it as subtraction, that would be fine. Okay. The reason it was addition to start with is because it was representing the number 18. Yeah. All right, so I don't have any problem doing 30 minus 10, right? But I have a problem doing 4 minus 8, especially if I'm not understanding that there's these things called negative numbers yet, okay? So what do we want to do? Well, one way to deal with it is to do this idea of borrowing, and this is what this is, right? It's an expanded, right, this guy is just driving me crazy. Oh, that's not what I want. Okay. The idea of having, the expanded idea is to have an idea of borrowing something. So when I borrow from a number, I take this number, in fact, let me do the standard algorithm down here so you can see what we do when we do this. All right, so when I have taught or learned the standard algorithm, what I say is I can't take 8 away from 4, I have to borrow. So I take my 3 and I turn it into a 2, and my 4 becomes a 14. And you may or may not write the whole 14. You may write the number 1 beside the 4 and small or something like that. But 14 then minus 8 is 6, and 2 minus 1 is 1. All right, so what did we do when we took the 3 and we turned it into a 2? We took actually 10 away, didn't we? We actually turned 30 into 20. I mean, that's what we really did. And then we turned the 4 into a 14. What we really did is we just regrouped. We moved 10 from here over to here. You guys see that? But I don't know about you, but I know that my daughter thinks it looks a little bit like magic. Right? I mean, we just moved some numbers around. And the problem is if you don't know how those numbers or why those numbers moved, then you might not move the numbers quite right. And this gets even worse when we get to multiplication. It looks a little bit even more like magic in multiplication when we do it. So we have to have this understanding of why we're doing it. And so for a kid who always does it right, it's probably not that big of a deal that they know why they did it. But for the kid that's continually doing it wrong, they need to know why we're doing it. Otherwise, they're never going to remember how to do it properly. Make sense? All right. Then we're able to do our subtraction. You can actually move left to right or right to left after you've done your borrowing, right? So if you wanted to do 20 minus 10 and do that piece first, you could. That gives you 10. And then the 14 minus the 8 gives you the 6. And you could actually then write that this is 16 in condensed form.
So how would you explain to them why?
You could do it with a concrete model. This idea of what I had to do kind of with what over here, right? I had to actually take 10 away from the longs and turn them into 10 individuals. And that's what's happening on the expanded model when I'm doing this, or even the condensed model. I'm taking the 30 and I'm turning it into 20. And then once I have that 20, where did that extra 10 go? It was grouped with the 4 originally. You can also do it pretty well with money. Money's not the root of all evil, it's the love of money, just in case you were curious about the Bible saying, right? Verse in the Bible says the love of money. Money is a great teaching tool, because if I were dealing with this and I had $30, that would be 3 tens, right? It'd be really easy to take one of those tens and to turn it into 10 ones. Okay, so ignore the 5, he's not helpful at all in this discussion. But if you turn the 10 into 10 ones, then you actually have 14 ones that you can remove something from really well. So you could do it in any of those kind of concrete ways to start establishing that idea of the relationship between our symbols in concrete sense. Come on. All right, equal additions is a really fun one. All right, so equal additions, what it does is it eliminates the need to borrow. That is the whole goal. So I want you to write that on your paper. The goal of equal addition is to eliminate the need to borrow. There is no borrowing in equal additions. Okay, it eliminates the need to borrow. And it does it by equally adding values. So, if I have to subtract the number 158, I'm almost subtracting what? I'm almost subtracting 160. So I'm actually going to take that 2 that gives me the 160, but if I add a 2 on the bottom, I'm going to add a 2 on the top. And these numbers turn into 836 and 160. Okay. The value, the result didn't change, but the numbers changed a little bit. Okay? But if you'll notice, if I actually try this subtraction, I still have to borrow 1 because the 6 has a 3 above it. Not so good. Okay, so I'm not done here because I would not have eliminated the need to borrow. Okay? So I want to take the number 160 and to turn it into something else that's easier to subtract with. What could I turn it into? What is that? 200. It would be better, or at least a little bit easier, to subtract 200 from something than to subtract 160. So what would I have to add to 160 to turn it into 200? 40. But if I add 40 to the bottom number, I got to add it to the top. So 836 plus 40 is 876, and 160 plus 40 is 200, because that's my goal. And then I can subtract with no need to borrow. So what is 876 plus minus 200? 676. Okay. One question that I sometimes get asked is, could I have taken the 158 and added 42 from the beginning? And the answer is yes. If you see, oh, I'm missing 42. I added sort of make it a one-step process instead of two-step process. Sure, you can do that, that'd be fine. But either way you do it, you end up at the end with the 200 that you're subtracting. And the goal was to subtract with no need to borrow, and you did that. Okay? I will actually do this sometimes. Usually the numbers that I have when I'm trying to do something in my head and subtract involves number 9. I don't like dealing with 9s. Subtracting 9s is no fun. It is much easier to subtract 10 and add 1 back when I'm done. This is what I do. I use equal additions in my head a lot when I'm trying to figure something out. Okay? If I have a calculator, what's the point? Okay, remember the point is your kids don't have a calculator when you're teaching them this. Keep that in mind. You're trying to eliminate the need to borrow on this one. All right, we're going to talk about some phased addition. And I was talking with a couple of you last time when you left class about, when would I use this or how would I use that, or we were talking a little bit about finding the numbers before and after in historical basis when looking at Egyptian numeration or whatever numeration I asked you questions on the test, which is two questions. And part of what we're doing in this class is trying to get you to think about something that's difficult for your mind to produce. Okay? And the reason for that is addition for you at this point is not difficult. Right? I mean, addition's not hard. You've been doing it for about, I don't know, 15 years, some of you. You've been doing this for a really long time. So what we're trying to do is trying to put you back in the mindset of the 5-year-old or the 7-year-old or the 8-year-old or whatever who's in your classroom and they're encountering this in the first time. And it's a little bit difficult because they don't think the way that you think about it because they haven't been doing it for 15 years or 20 years yet. Okay? So that's kind of where we are with this. Are you going to teach kids how to do something in another base? Probably not. If you have the GT gifted and talented kids, they might encounter something like this because it looks like fun. Okay? You're probably not going to work with those kids most of the time. Okay? So, again, the point is to put yourself in a position that makes it a little bit challenging for you so that you can feel like what your kids feel like when they encounter some of the addition that's in our base 10. All right. So, other bases. We're going to talk about base 8 first. So, base 8 would be like the idea that would happen if when you were born without thumbs. I mean, like we would have all had to have been born without thumbs to make this work. But if you only had 8 fingers, you would probably have a system that was base 8. We have base 10 because we have 10 fingers, and that's the reality. The reality is we work at base 10 because we have 10 fingers. If we were only born with one hand, we'd probably be working in base 5. Okay? So we're going to look at base 8. All right, so in base 10, we have 10 numbers. What are they? 10 numerals. We actually have 0 through 9. We do not actually have a 10 in base 10 as a single numeral. And we have something we call a 10, but it's not a single numeral 10, right? Okay, so what do you think happens in base 8? How many numerals do we have?
7, 8.
We have 8 numerals, but we start with the numeral 0 and we end with 7. Okay, so the numerals go from 0 to 7. Okay? So there are no 8s, there are no 9s in base 10. I mean, I'm sorry, there are no 8s and there are no 9s in base 7. Okay? 0 through 7. Everybody good? What did I write something wrong?
No, I think you said base 7.
Oh, base 8. I probably did this wrong. In base 8, there are no 8s in it. Well, there are no 8s and 9s in base 7 either. But yeah, in base 8, there are no 8s. Okay. So I'm going to show you what we do in base 8 when we add. And I'm going to show it to you in a couple of ways. One way I'm going to show it to you is with your hands. Okay? So guys, got all hands. Got all hands. I'm hands. You got hands. All right. We're starting on the right-hand side with the 4 plus 7. So when we add 4 plus 7, we know from materials we've been working on, it doesn't matter if I do 4 plus 7 or 7 plus 4, right? Right. So we kind of tend to start with a larger number and add up from there, which was one of our methods that we learned back in 3.1 was the add up method. Start with the biggest number and add on to it. All right. So what we're going to do is we're going to start with 7, and in my mind I'm going to add 4 more numbers to it. Okay? But I do not have a number bigger than 7 in base 8, correct? Okay. So when I add the numbers, I can't go, like what we would do in our systems, we would go 7, 8, 9, 10, 11, wouldn't we? 8, 9, 10, 11, 8, 9, 10, 11. We just add the digits from our fingers to it. So what do? Well, we need to know what comes after 7 in base 8. 1, 0. And we keep going until we get to where? 1, 7, and then it would become 2, 0. All right? So what's happening is we run out of digits. And when we run out of digits in our base system, it becomes a 2-digit number. Correct? But when you run out of digits in base 8, it becomes also a 2-digit number. All good? Okay. So right now we are at 7 because I'm adding 4 plus 7. So we're at 7. So I don't go 8, 9, 10, 11. What comes after 7? 1, 0, 1, 1, 1, 2, 1, 3. This is the number 1, 3. 7 plus 4 is 1, 3. What do I do with 1, 3? Well, I write a 3 down and I carry a 1. That's the standard algorithm, right? I write a 3 down and I carry the 1. I carried the 1 because I had 1 8. That is an 8 that I had too many of. And that's why it's in the 8 column now. Okay? Now I have 1 plus 3 plus 1, which is all smaller than 7, so I'm happy enough to just add that. 1 plus 3 plus 1 is 5. The answer is 5, 3, but it needs to have the base 8 as a subscript written beside it. Otherwise, if you do not have a subscript written there, it is assumed to be base 10. So make sure you write your subscript on there. So this is 5, 3, base 8. Okay? Now, you might think, what am I doing here? No, I'll do it in the next one. Let's do subtraction, and I'm going to show you why in the world we might like that add-up method with subtraction. Okay, same problem, except it's subtraction. It's actually 3, 4 minus 1, 7. All in base 8. Okay, so here's the deal. I can't take away 7 from 4, right? So in our number system, we have to borrow, and we can borrow in base 8 just as well. Then take the 3, this is actually 3 8, so this is like having 3 long strips that are all 8 long. So when I take one of those strips away, I don't have 3 of them anymore, I have 2. So the 3 still becomes a 2, just like for us. But when I take that one strip of 8 long, and I add it over here to these 4 that I have, I do not have 14. I have 12. Why do I have 12? Because I only had 8 in the strip. Or can you imagine a picture? Like you take the strip and you actually cut, like a little piece of paper, right? You cut it into 8 little blocks now. So this 8 little blocks plus the original 4 little blocks means I have 12 blocks. Got a picture of it? So there's actually 12 here. Once I get to this point, it actually subtracts just like our system. But the changing that, the borrowing part's the part that's different. So then I have 12 minus 7, which is 5. And I have 2 minus 1, which is 1. So this is 1, 5, base 8. Okay, so this works fine. We can do the borrowing as long as we remember what we're borrowing. Okay, but you have to really understand what borrowing is to do that, don't you? You can't just tack on a number 1 like you could with base 10. You have to really understand what borrowing is. I want to show you what equal additions looks like here, because I think it's helpful to have a perspective here for why it's a nice method. Okay, remember what's the goal of equal additions? Not have to borrow. The goal is to not have to borrow. Right now, problems written we would have to borrow, so that's no good. So what would I have to do to this to get this to not have to borrow? What would I have to add down here to mean I do not have to borrow? 1. Why 1, Brendan? Right. The number after 1, 7 in base 8 would be 2, 0. That's just 1 more. Okay, so the 1, 7 became 2, 0. What does the 3, 4 become? 3, 5. All of this is in base 8. You don't have to write it on your terms in the middle of it, but you better write it at the end. 3, 5 minus 2, 0 is 1, 5 in base 8. That's nice. Right? That actually works really well. I don't have to worry so much about the whole borrowing and how much am I borrowing. I just have to know that after the 1, 7 comes 2, 0, so I can add the number 1 to get that to happen. Okay. Let's do base 3, because that's fun. Alright, base 3 is interesting because it doesn't have very many digits. How many digits does base 3 have? 3. What are they? 0. So no 3s or 4s or 6s or 9s. None of that's happening in base 3, right? I have 0, 1, and 2. All right, so I have the number 1, 2, 1, 2, base 3. And I'm supposed to be adding. So let's do the addition. Oops, I already wrote it wrong. let's do the addition in a standard old addition like, oh dear. Make that go away. Our standard old algorithm that you know. 1, 2, 1, 2, 1, 1, 2, lined up. But in order to do this, I need to know what comes next. So what comes after 2? 1, 0, and then, and then, and then, all right, I'll stop. Yeah, 1, 0, 0. I know this is the last section, so but we have to know what comes next, right? Okay, so let's take a look here. If I add 2 and 2 together, well, I'm starting with the 2, right? And after 2 is 1, 0, and then 1, 1. So I'm going to write a 1 down. I'm going to carry a 1. Now I have to add 1 plus 1 plus 1. Well, if you're following along, kind of like a number line perspective, if I start out at 1 and I add 1, I get 2. And if I add 1 more, I get 1, 0, right? So I'm going to put the 0 down here, and I'm going to carry my 1. Now I'm going to add 1 plus 2, so I'm here at 1. I'm going to move over 1, 2 spots, so it puts me at the 1, 0. And then 1 more, which puts me at 1, 1. And sometimes students really like number lines, which is kind of what I'm doing over there, isn't it? I'm treating this very much like it's on a number line, and I'm just jumping spots on a number line. Some students really like number lines. Last one is 1 plus 1, which is 2, and the answer to all of this is in base 3. I'd like to show you before I let you go the lattice for this one. Okay, so let's do the lattice right here. It's not on the next slide, I'm sorry. I was just going to do it right here. I did not indicate on the problem how you had to do it. So I'm going to show you what it would look like in lattice. All right, same idea except that I'm not going to actually do as much, well, I'm not going to do any carrying. If I have the two 2's added together, it's very much like I have the 2 2's added together over here. Number line perspective or adding on your hands, right? So if I'm at 2 and I need to know I had to add 2 more, 2. After 2 is 1, 0, and then 1, 1. There's 2 on my hands. I've added 2 to the number I started with, so that's 1, 1. I add the 1 here and the 1 here. And it's 1, 1 in the 2 separate boxes. Add 1 plus 1 is 2, so that goes in the bottom box down here as a 2. I have a 2 plus a 1. Well, I don't have a 3, so that's 1, 0. And then this 1 right here comes straight down as 1. All right, so with lattice, we're adding diagonals together. So the first diagonal has a 1 in it, so I write the 1 down. The second diagonal has a 2 plus a 1, and in base 3, what's 2 plus 1? 1, 0. So I'm going to write down the 0, and I'm going to carry the 1 over. So there's my carrying that you see. You do sometimes see carrying in lattices. I've got a 1 and a 0, which is a 1. I've got a 1 and a 1, which is a 2. Oh, good. I'm glad I've got the same answer. This is base 3. All right.